The next strategy that we're going to consider here is looking at special cases. Um, Sometimes it's helpful to look at special cases of a situation where we can find a pattern that we can then use in another problem. So we're going to look here first at Pascal's triangle. And Pascal's triangle is rather simply created. You start with a 1 in the top of your triangle, and then underneath it, so if I just look at these top 3 here, you put 2 more 1s. And you're going to always have 1s on the outside. Then to find numbers in the middle, if you will, of the triangle, what you do is you add the 2 numbers above that number. So this 2 comes from adding 1 plus 1. The 3 here comes from adding 1 plus 2. If I come down here, let's look at this 15. That comes from adding the 10 and the 5 above it. So when you're dealing with Pascal's triangle, it's the numbers in the middle, again, are just formed by adding the 2 numbers above it. And what this gives you is the number of ways to reach that certain point. So for instance, if you look at the 6 right here, this means that there are 6 ways, starting at the top of this triangle, there are 6 different paths that you can follow to get to the 6 here. I'm not going to go through all of the different paths, but I'll trace a couple of them. So again, starting at the top, one of them is to go down the left and over. But you could also go to the right and kind of do a little bit of a zigzag pattern. But there's 6 different ways you could reach the number 6. So that's what these numbers are also giving you. So that should make sense down the sides. If you're starting from the top, there's just one way to reach these, because one thing I failed to mention a moment ago is you're not going back up, okay? There'd be an infinite number of ways if you could go back up and make loops. But if you have to keep going down, okay, if you're just going straight down the left or straight down the right, and you can only go downward, there's only one way to go down that side. So let's look at a special case. It says, if one must always move downward along the lines of this grid shown, how many different paths are there from point A to each of these points? So this is a variation of Pascal's triangle. We actually don't have quite as many intersections as you would have in Pascal's triangle. So we're going to go with the same process as Pascal's triangle is formed. You've got a 1 here at the top. So A has got a 1 next to it. And each of these intersection points along the left and the right-hand side are going to also have 1s attached to them. Because if you can only move downward, there's only one way that you can reach these. And you would have the same thing on the right. And then to fill in the middle, it's just like Pascal's triangle, you're going to add the 2 numbers above it. So this point right here, the point above the B, if you will, 1 plus 1, this one has a 2 attached. So then if I move down here, okay, I have a 1 and a 2, so this one is going to have a 3. This point here, okay, so kind of above the C. This is a little bit of a trickier one. Because this point here only has this one path to reach it, okay? There's no line here. So I'm not going to add the 2 plus 1 to get here. The only thing that has a direct path to it is the 1. So this one is just going to be another 1. Okay, and again, that's because I don't have a path drawn to this point here. Now, B and C. B is 3 plus 1, so B is 4. So there's 4 ways to reach point B. For C, 1 plus 1 is 2. So now we need to get to D and E. So I need to fill in a few more of these intersections. So I'm going to come over here to the left. So this point here, I've got a 1 above it, and then I've got this 3. So both of these paths reaching it. So I've got a 1 and a 3, so this one is going to be a 4. This point right here, so coming down, so kind of down into the left from the B, there's only one path leading to it, so it's just that 4 again. And then moving over, so this path downward and to the left from C, again, there's only one line leading to it, so there's going to be a 2 here. So we're almost able to do D and E. I need to just fill in a couple more intersection points. So I'm going to go right here. So this point that's up and to the left from point D, we're going to have an 8 there. Then here, 4 plus 2 makes 6. And this point over here, again, there's just one line reaching it, so I'm just going to continue that too. So for D and E, D, 8 plus 6 is going to equal 14. E, 6 plus 2 is 8. So there's 14 ways to reach point D, only 8 to reach point 8. Or sorry, only 8 to reach point E. And we're going to look at one last example here in these notes. And this is related to arguing from a special case. So when you're arguing from a special case, you're making an argument from either a special case, like with Pascal's triangle, or a similar problem. And we can use this to come up with a path or general principles for solving a more general type of problem. So again, that's what we just used. And then the second definition I have here is an arithmetic progression. And in an arithmetic progression, you've got a very special type of sequence. It's a sequence where going from term to term down the line is found by either adding the same number or subtracting the same number. So we're given the sequence 8, 5, 2, -1, and then it's going to continue till we get to the number -52. And we're asked, is this an arithmetic sequence? And in this case, it's going to be a yes. In this case, you are not adding but subtracting to go from term to term. So 8 to 5, you're subtracting 3. 5 minus 3 gives you 2. 2 minus 3, -1. Even though it's not written, the next number would be a -4. -1 minus 3, -4. And you would continue. If you wanted to, you could write out all of the numbers in the sequence from 8 to -52. You could write them all out. There's not an overwhelming number in this sequence that you couldn't write them out. But there is a shortcut to find the number of terms in the sequence. So again, yes, this is an arithmetic sequence. The constant difference in this case is a -3. And then the second question there, how many terms are in the sequence? So, like I mentioned a moment ago, you could write out the entire sequence, totally fine, but there is a shortcut. To find the number of terms, what you can do is take the last term in the sequence minus the first term. So that's negative 52 minus 8. So that gives us negative 60. So subtract the last term minus the first, negative 60, and then you're going to take that negative 60 and divide it by the constant difference. So negative 60 divided by negative 3, and that gives you 20. Then you're going to add 1. So how many terms are in the sequence? 21 terms. Oop. It works much better if I box in the whole thing there. Sorry, y'all. So there's 21 terms. So we add the 1. This kind of harkens back to the problem with the fence post where you've got that starting post and the ending post. So it's 1 more than you might think it would be. That's that plus 1 there at the end. But this process works when you've got any arithmetic sequence and you want to find the number of terms. As long as you have a distinct starting and ending point, you can follow this pattern. So again, you're taking your ending number minus your starting number, dividing by the constant difference, and then adding 1. So that gives us the number of terms.